Good afternoon, late good afternoon to everyone. My name is Alok Bhardwaj, and I'm an assistant professor in the Department of Civil Engineering. And today, in this series of lectures, I'm speaking on understanding urban floods using Earth observation and AI. And you can also see on the screen, we have our research group by the name of Hazard Busters, and we are active on LinkedIn, Twitter, as well as on YouTube, and we are growing our group. So please subscribe to this, and we always keep posting research from our group, interesting videos related to Earth observation and AI, and so you can always come back to this to our group on different social media outlets, and you can see that what we are doing. All right. So let me just start this presentation by defining disaster. So according to UNDRR and Center for Research on the Epidemiology of Disasters, also goes by the name of GRID, they have defined disasters that refers to a serious disruption of society by unforeseen and often sudden situation or event which exceeds local capacity to cope with using its own resources. And generally in India, we are faced with different type of disasters, ranging from drought, earthquakes. We face storms on our different coast, floods in different parts of our country, landslides in the Western Ghats, in Northeast, as well as in the Himalayas. And at some places, we also face fire. And recently, we were also hit by the COVID-19 pandemic. So today we are understanding, or we are discussing on the floods in particular. And if you see that flood among all the disasters is the most influencing one, is it causes the largest damage given all the disasters that are there. And you can also see the numbers, which has been published by GRID in 2015. So around that time, around 2.3 billion people across the world were affected by the flood disaster in the year between 1995 and 2015. So it is really essential to understand about flood disasters. All right. And in particular, to understand about flood disasters in an urban setting, because most of us live in urban areas, and the susceptibility of the people and the economic elements are more in the urban areas. So we need to identify, or we need to understand about urban floods, and how can Earth observation and AI can help us in understanding it better. So here is an example of using Earth observation for floods. So this has been taken from one of the papers that has been published. Uh, uh, so it says that the flood extent maps of the Houston study area. It also shows you the binary flood extent map on using one of the Earth observation data sets. We call it as SAR, synthetic aperture radar, and they are using its intensity and coherence to understand or to map the extent of the floods in this urban area. All right. So you can see that you can, using certain Earth observation data sets, you can map the extent of the floods. This is another paper that I am referring to, not from our lab, but so the link is being given at the bottom. So it gives you an overview of the model training pipeline which is used in this work, and it basically uses data from the different data sources, and it then generates the flood shape files or the metadata, and also uses the Sentinel-2 image. And then it applies some segmentation models that comes within the purview of the AI models. And then it is finally able to predict the flood extents. So through the studies, what I'm trying to do is I'm trying to bring your focus that in today's time, Earth observation data uh, is available in an easy approach. You can always get the data, and also the different type of advanced AI models are available, and you can always combine the two to get better and better flood extents for urban areas. So this study was done. I am one of the co-authors in this study. So what it shows you that to understand about urban floods in a given area, you need to have optical data sets, and these optical data sets are really essential to get, and because it tells you that where the flood has happened. So in the left figure, you can see the brownish part in the center of the image that shows you that that is the flood affected part of this particular area. And on the right hand side, you can also see synthetic aperture radar or the SAR dataset, and it is basically an intensity image, SAR intensity image that shows you the flood that has happened. And at the center, you can also see the big W that is there. And this particular big W, let me just also use a color. Right, and this particular W and some other dark areas actually helps you to understand that these are the flood affected parts of this particular region. So always you can always use these such kind of Earth observation data sets. It can be optical data set. You can also use very high resolution data sets. Usually we need to buy those data sets, but those are available uh, uh, for understanding about floods. And of course, the SAR data set is there. And these SAR data sets are available from the Indian uh, space agencies, ISRO, and is also available from European Space Agency, and some are also available from NASA. So you can always use a combination of these two data sets to understand better about the urban floods in a given area. Now, having an understanding that you can use these Earth observation data sets, you can always apply different type of methods. So the lead author in this particular paper applied the approach of probability of identifying the flood in a given area, and they were trying, and we were trying to identify that what is the probability of identifying a flood extent in a given area. And on the legend, you can see that to have a very good detection or to increase the accuracy of your flood estimation, you also need to have better training data sets. So you can see that these basically these are called as labels. So these are handcrafted. So you can identify these are floods, permanent water, flooded vegetation, dry vegetation, these are dry areas, uncertain areas, right? And there are also floods having low intensity and high intensity portions. All right, so you can always apply certain methods on these particular Earth observation data sets to identify the flood extents. So in general, so what we have seen so far, in general, we can use Earth observation to understand about urban floods. And generally, mainly we are using two types of data sets in Earth observation. One are optical and the other is SAR. All right, so in this particular slide, you can also look at one of the images on the top left that is a SAR intensity image, which is acquired during the flood. And on the bottom, you see this particular figure that gives you an illustration of the different backscattering mechanisms of these microwaves that interacts with the different elements on the Earth's surface under flooded conditions. And for different land covers, suppose if there is a bare soil is there, vegetation is there, built up areas are there. So you can see that in this particular area, so it is microwaves are interacting differently with the ground surface. Here they are interacting differently, and here it is volumetric scattering that is happening, and here you can also see the double bounce is happening. All right, okay, and it is returning back to the satellite. All right, but here it is returning. It is being scattered away from the satellite. So these are different interactions that are happening when these particular waves that are coming from the SAR sensor interacts with the elements on the Earth's surface. So there are certain challenges that we need to encounter and solve if we want to use Earth observation for flood mapping in urban areas. And it basically deals with understanding about the scatterings, different scatterings. So one is the double bounce scattering that is happening. Other is the roughness that arises on the water surface due to the winds. Suppose if this is your uh, surface which has been flooded, so either it is a still water, it's still area which is being flooded and the water is still, or generally whenever flood happens, so they are being uh, uh, they come together with winds, right? So the winds may roughen this surface. So if it roughens this surface, then it means that the interaction of the waves with the surface becomes different. All right. And the third is about the surfaces that have water-like reflecting properties. For example, roads are there. So roads are made up of coal tar, tarmac, and they almost behave as if the water is there, because whenever a wave is coming, and if there is a road, the wave is scattered away from the in direction from which the signal is coming from the satellite, and it behaves as if there is a water. So we need to also face this challenge of how do we differentiate such kind of surfaces from the water or the flood water that is there. All right. So to do this, we can always take the help of AI models. And here we are giving you an example of a 1D CNN. So 1D means it's one dimensional. It means the data is only within one dimension that is there. All right, it's not an image, it's a time series. And the other is it's a CNN convolutional neural network. So these are one of the important networks or AI models that are there that can help you to understand better about or detection of the urban fields. So we can always apply this kind of model to the input data sets. And what are the input? You can always have the SAR intensity and the SAR coherence as the input. And it goes through this particular architecture of the 1D CNN. And then finally, you have the output. And what are these outputs? The outputs are whether for that particular pixel, have you identified it as a flood or you have identified it as non-flood, right? And you are making these labels, and these labels help you. If you make the labels very accurately, these labels actually help you to increase the accuracy of the detection through this model. All right. So finally, you do the detection, you do the prediction, and the prediction of flood extents. All right. And this kind of map, it actually doesn't look like it's a flood map, but this shows you that how your model is performing. All right. So the true positives imply that these were actually flooded, and your model has also identified that these are flooded. True negative implies that it is not flooded, and your model has also identified it as non-flooded. All right. And false positives or false negatives imply that it was flooded, but the model didn't identify it as flooded. Or the other situation is if the pixel was not flooded, your model has identified it to be flooded. And you are using these gray portions as training data and the black portion as validation data. All right. So this should be the de facto or the standard to show that how your model is performing if you're using an AI model on the Earth observation data sets to do flood detection, and particularly in urban areas. So if you're able to show this kind of map where true positives and true negatives and false positives and false negatives are shown, then that implies that you are showing the results in the correct manner, and one can easily determine that what is the accuracy of your model on that particular on that using that particular Earth observation data set to detect the flood extents. So this is another study that one of our research scholars is doing in Thailand, and they are trying to understand the flood that happens in this particular area, which goes by the name of Pitsanulu. And the problem in this area is that it usually gets flooded every year. And we selected this particular event because we had almost simultaneous uh, occurrence of optical and SAR data set. So they were almost acquired at almost the same time with a little bit of time difference between the optical and the SAR data set. So you can see that we have a very high resolution optical data set for this event, and we also have a concurrent SAR data set. And they are having a difference of only a few hours. So this is a very good candidate to understand that if you want to apply a certain AI model on this, and so you can always test the accuracy of that AI model. You can always train that AI model on the SAR dataset because you have an optical dataset with almost a similar time frame with the SAR dataset, and you can generate your labels on this optical dataset. All right. So what we did was that we applied certain computer vision models to this. So one of the computer vision model is, or the computer vision method is thresholding. So we applied the Otsu's thresholding on the SAR dataset, and it detected, as you can see on the screen on the right hand side, either it is flood or no or non-flood. And then we can always overlay this output from the Otsu's thresholding or given any other given method, and we can overlay that with the labels that is being generated from the optical data set. And then we can understand that what is the accuracy of the detection of the floods using a particular computer vision method. So here you can see that it is able, so the white part shows flood. So it seems that it is able to identify the floods, and it is able to identify the flood extents, right? So you can always compare. So it is a visual comparison in the presentation, but we can do a quantitative comparison also by overlaying one with the other in a GIS environment, and then generating certain evaluation metrics such as CSI or F1 scores. All right, this is the result from the k-means thresholding. So the k-means thresholding, it works. So the k-mean works as a clustering technique, and it is also giving you a result almost similar to the Otsu's threshold. This is another method that we used, and which is called as the textural analysis. So the textural analysis basically tries to identify different parameters in a given image, such as mean, variance, all right? And then it tries to build these different images of the mean and the variance, and then it tries to connect them and try to identify and come with a rating. And in that manner, it tries to identify the flood extent. And here you can see that this textual analysis is over predicting the flood extents. All right. And so visually, it seems that it is giving you us much more flood extents than much more flooded areas than actually it is that is there, right? And this is the morphology. And this particular function basically tries to expand or erode a certain pixel so that it is able to identify these flood extents. And it is basically, this morphology is basically used with the active contour model in this, with this data set. And you can see that it is also able to identify more or less the same areas which are being flooded. So in that manner, you can always apply these different computer vision models to identify the flood extents. So the particular research scholar is also working on combining all of these methods together to come up with a new rating technique to increase the accuracy of the flood detection. The second work that is being done in our lab is related to the application of SAR polarimetry. So in this particular case, we are using the dwell pole data from the Sentinel-1 SLC datasets. And as you can see on the left-hand side, so this work is also being done by one of our research scholars. So you can see on the left-hand side, first of all, this particular dataset is being processed in the SNAP software. And then the output is taken to the PolSAR, which is another software available in the public domain to work on the SAR polarimetry. And finally, it extracts certain parameters which is related to like Stokes parameters and the eigenvalues. And ultimately, what this polarimetric decomposition helps you to understand is to identify the different type of scatterings that are happening on the ground. And it can range from double bounds to volumetric scatterings. Because ultimately, if you know what kind of scattering is happening on the ground, you can identify that what kind of land cover that is there, which can ultimately help you to understand that what is the, that where you can expect the floods and where you cannot expect the floods. So this polarimetric approach actually helps you to reduce your false positives and false negatives. So here you can see that one of the outputs is the eigenvalue output that is for the flooded date that is there. And the second one, Fi indicates, so here Fi is written here, so this indicates flood index. So this is based on this particular eigenvalue. And here this Fi value goes from 0 to 1. And it shows you that wherever it is 0, there's a higher chance of being flood. Wherever it is 1, there's a lower chance of being flood. So the darker region shows you the flood extents. And this study area is basically in Japan. And in Japan, it is in the Hagibis flood that happened in 2019 that caused widespread damage in Japan. And here you can also see that we also obtained the PDAS data, high resolution PDAS data for this particular flood event. And you can observe that for the flood index that it is being shown here, it actually shows you the flooded, the flood extents that you can also observe in the optical data set. So it is able to identify this. So we have not shown you the accuracy assessment, but it seems that the F1 score comes close to about 0.7. And that is a good indication of that you are able to reduce the number of false positives and false negatives. Also, in this particular portion, you can see that there are certain portions which looks dark are flooded, and the same portions are also being flooded here, right? In this, which you can visualize in the high resolution image. So this is another kind of Earth observation data set, and this Earth observation data set is basically the SAR data set itself, but we are exploiting the scatterings mechanisms of the SAR data sets by employing certain polarimetric decompositions on the data set and trying to come up with a certain index to identify the floods. And we are also doing certain accuracy assessment with the optical data set. That is it. All right. So in general, if we look at understanding floods using Earth observation and AI, we should also look at that what is the intricacies that are involved in understanding the flood, because ultimately when you understand about flood extents, it leads to understanding that how better you can respond to floods. So if you can see here, it shows you an overall causal loop of flood pathways. There are certain green curves are there, which refers to normal conditions. For example, a flood is there. Now the flood can be connected to a reservoir can be connected to a green patch or a green area. which is connected to a river or sea level. Amber or orange refers to caution for probability of flood mapping, right? So there is a match or a connection between reservoir and volume signs, all right? And this is also related to the emergency services. And the red refers to a very high risk or the event of flood map. All right. So on the left hand side, you can see basically the sorry, you can see the causes of floods that are there. For example, evaporation could be one, rain and snowfall could be one, where you are geographically located, soil temperature and moisture. All right. These are the impacts that the flood has on energy infrastructure damage, on business impact, on farming damage, right, on social impact. And how are these, all of these are connected? So if we really want to do a good flood response, we really need to understand each of these factors, need to collect data for these factors and try to understand that how one is connected to another. So in doing so, always we can use, in addition to Earth observation, we can always use data from the social media. And it has been defined in literature that this is also known as the hyper-resolution data. So for example, if you have a canopy, for example, right? So if you can see here, there is a canopy, right? And if it is so dense that only the SAR can penetrate through canopy, but if you have given, say, C wavelength, so it cannot penetrate the canopy. But given if you have P and L wavelength, then that has the capability to penetrate the canopy to a certain extent. So it sometimes so happens that you are able to identify the flood extent in open areas, but what is the situation below the canopy? So, for example, whether any road or any area is being flooded under the canopy or not. So this information is usually not available. So if you can get such kind of data set from social media for your own area, you can always validate your results to make your models more accurate. All right. So such kind of data, which you can get under the canopy from the streets or the street views or the street images that are there, always helps you to increase the accuracy of your flood detection using AI and Earth observation. So one of the examples that people have used is that this is, I think, part of US. And here you can see that it shows you precipitation. So this area is having a lot of a very high precipitation, and it is correlating directly with the number of tweets that is happening in this area. All right. Okay. So you can always see that this this particular area, the people are tweeting a lot, and they must be saying that a flood is happening, or a hurricane is coming, or a high rainfall is happening, and that is correlating directly with the precipitation. So you can always always issue a warning that this area might get flooded. All right, so it's a link between observed precipitation and tweet volume. So one of the questions that one can use is that how AI can be used to classify these tweets with the flood context. All right, but sometimes you know that people just write the tweets where they use flood, not in the context of what we are understanding, but maybe in other contexts. It always is a problem that how do you classify these different tweets, and then from those tweets, how you can predict that that particular tweet is related to flood or not. All right. So it has been seen in the recent years that the application of the machine learning in flood detection has increased tremendously. And these are the number of articles or the number of research papers or conference papers that shows that there has been an increase in the number of the papers that are using these AI methods to detect floods. And in particular, people are interested to use ANNs. All right, because more and more data is available, so the ANN can justify the influx or the input of such data sets. All right, and it can understand better and better patterns from such data sets. All right. So I tried to show this slide that shows that one should have a caution in using AI for disaster response, and particularly for floods, because training data is a major component of the AI pipeline. If you have a good training data and you are using a simple model, it can give you wonderful results. But if you have a bad data and you are using a very sophisticated model, it can give you not so appreciable results. Second is collection and documentation of training data is really essential because usually we do the work and we never document the work enough so that it could be used by other people. All right. So collection and documentation of training data is of utmost importance. And this is usually the main bottleneck in the application of AI-based techniques for disaster response. And the second is class imbalance is often encountered in training data sets, and it should be managed in the training data. So for example, I can give you an example. So suppose if I can take this area, this particular area, so you can see that only this particular portion is being flooded, right? Mostly, right? If you zoom in and then try to make labels, so the situation might be a little different, but more or less say this area is being flooded. And the other area is not flooded, right? Okay. So you can see that now this other area is not being flooded. All right. Okay. But when you're generating these labels, you're generating the label for your whole study area. So it will have labels for flood as well as for non-flood. But it might so happen that the flooded portion are having a fewer pixels than the non-flooded part in this image. So the flood pixels are fewer in number than the non-flood pixels. So there is a class imbalance because there are two classes and there is an imbalance of one and other class. So what happens is that the class which is having higher pixels, the AI is trained to detect those pixels. So it so happened that if you have floods, labels are fewer in number and non-flood labels are higher in number. So you might be thinking that you have designed an AI model to detect flood, but actually it is designed to detect your non-flooded areas. So you need to check whether there is a class imbalance, and you need to prevent this class imbalance in your work. Okay. So as I said, so the challenge here is for the generation of the latest and the greatest training data or the label data. Right? For example, I'm showing you an optical high resolution image for the Odisha floods back in 2022. So on the left, you can see that it's a pre-flood image, and on the right, you can see it's a post-flood image. So what you can do is you can acquire SAR datasets. For this, you can derive SAR intensity and SAR coherence. You may also derive different colorimetric decomposition products for this. And then you can always input these products into an AI model, and you can get a certain output for flood detection. Or you can also use computer vision on single SAR intensity or coherence images. All right. But your accuracy will depend on how best you have generated your training or label data. Because if you have a good training or label data, that can help you to assess better how your model is performing, be it computer vision model or AI model. All right. So this is my last slide. It tells you that generating the labels or generating the training data is of utmost importance if you're trying to understand about urban floods in using Earth observation in AI. Okay, so I'm giving you an example here. So suppose this is a high resolution image. So on the right hand side, you have created a vector data set, and then you have converted that vector to a raster data set so as to use it in an overlay fashion with the SAR data sets, right? So because SAR and those are also in a way raster data sets, so you can overlay them and then you can do further analysis. All right. So so with that, I would like to finish my presentation and would like to say that there is a lot of scope in understanding about urban floods using Earth observation and AI in today's time. And it is really an exciting field to jump into and try to do very good work in detecting the floods with a very, very high accuracy. Thank you.